Hi, and welcome to this first video in the series on trigonometry, and in this particular video we're going to be looking at something called radians. So what we're going to do now is move your way of thinking away from measuring angles in degrees to looking at another way of measuring angles, which is this idea of the radian. So radian is another way of measuring angles in the same way that we could use centigrade and Fahrenheit for measuring temperature. We can use degrees, or we can use radians for measuring angles. And as you'll see over the course of the next few videos, and particularly when you get onto calculus with trig stuff, you're going to find that radians make life a whole lot more simple. So, first things first, what is going on with this whole degrees or radians thing? First thing to think about, just for a second, is why is a degree a degree? You know, we know that a degree is 1/360th of a circle, but why choose a circle and chop it up into 360 little bits? There's no real specific mathematical reason for that, other than that it just makes calculations a whole lot easier because there's a shed load of factors that go into 360. So if you want to talk about fifths of a circle or twelfths of a circle, then the numbers remain quite nice and easy. But there's no actual real mathematical reason as to why we should pick 360. It might make sense, and in fact there is a measure called a gradient, which actually divides a circle into 100 equal bits. We're not going to go anywhere near that one for now, but there is a genuine mathematical reason behind the radian, and that's one we're going to look at now. So, essentially, the radian comes from this shape here, which is an equilateral sector, and it's part of a circle. So, being it's part of a circle, we've got the centre of the circle is that point there, so therefore the two straight edges are the radius. And it's equilateral, so all three sides are the same length. So that means what we've got is the curved section is also of length r. Right? So what that gives us is that angle at the centre there is 1 radian, and we use a little c, kind of superscript c, to represent radians. Don't ask me why, I haven't got a clue. But that is the size of 1 radian. Now again, you might look at that and go, well, that doesn't seem to be particularly intuitive, or it seems slightly contrived, but trust me, it is going to make life easier, as we'll see on the next slide. First of all, let's just have a look at kind of how big a single radian is. Clearly it's much bigger than a degree, and we'll just have a little look at how many degrees are actually the same as a radian and what's going on. As it turns out, that idea of how many degrees make up a radian is not really an idea we need to worry too much about. There's much more obvious link-ups with certain other values, and again, we'll get to that. So, we know that if I wanted to work out the length of the curved arc on this section of a circle, then I'd work out whatever fraction of the full circumference it is. So I take my fraction of the circle. At the moment, I'm in degrees there. So, whatever size angle that is, divide that by 360, and then times by the full circumference of the circle. For this particular sector that we're looking at, this one over here, we know that the arc length, this bit, is r. So we can write that. So our arc length, r, is theta over 360 times by 2 pi r. And now we're going to manipulate this expression a little bit. So let's just divide both sides by r. So we end up with that. And what I'm going to work towards here is the size of theta. So if we move the 360 over, divide by the 2 pi, there you go, we've got theta equals 360 divided by 2 pi. And that's 1 radian, and when you do that calculation, you find that 1 radian is approximately 57.3 degrees, which again is a slightly bizarre number, not one that really you need to worry massively about, but it just gives you a sense of how big a single radian is. The easier conversion to work with, and this kind of link up between degrees and radians, is much easier when we consider, okay, we're saying that if our angle theta in this thing here is 1 radian, and we know, as we said before, that 1 radian is theta, 360 divided by 2 pi degrees. If I do a bit of moving around, that means that if 1 radian is 360 divided by 2 pi, then 2 pi radians is the same as 360 degrees, and that's the matchup that's easy to work with. And the next step from there is say that pi radians is 180. So if you remember those two in particular, then everything else follows on from there. And that link up there between pi radians being 180, 2 pi radians being 360 makes life a whole lot easier later on. So let's just have a look at some other angles. What I'm going to do is let's just pop those things on there, those things we'll talk about, and it might be a good idea for you now to pause the video and just have a bit of a think to see if you can work out what all those other angles are in terms of pi. And if you've done that, let's just quickly work through them. So 30 degrees, if we compare that to 180, that is 1/6 of 180, so 30 is going to be pi over 6 radians. 45, that's 180 divided by 4, so that's going to be 1/4 radians. And then what we're going to do is start building multiples of there. So we know that 30 degrees is pi over 6, so therefore 60 degrees, that's going to be double that, so that's 2 pi over 6, which is pi over 3. And then finally in this column we've got 90, which is clearly half of 180, which is pi over 2, or double 45, 2 lots of pi over 4, pi over 2, and there we go. Moving on to the next column, again all we're going to do is just work with multiples of what we've got in the previous column. So we know that 120, that's going to be double 60, so that one's going to be 2 pi over 3. 135, that's a multiple of 45, and that's 3 lots of 45, so 3 pi over 4. 150, we're going to use 30 to do that one, so 5 lots of pi over 6, 5 pi over 6. 225, we're back to multiples of 45 here, so it's 1 more than 180, so that's going to be 5 pi over 4. 270, that's 3 lots of 90, so that's 3 pi over 2. And finally 300, which we can have a go with 360 minus 60, so that'll be 2 pi minus pi over 3, so 2 pi being 6 pi over 3, so that's 5 pi over 3, or alternatively, clearly 300 is 5 lots of 60, so that would still be, whichever way you do it, 5 pi over 3. And like so, working with these, particularly with these common angles, if we express them in terms of multiples of pi, let's say as I keep repeating, it genuinely makes life easier later on. So let's just have a quick look at an equation where we've got to work in radians. So what we've got here is a quadratic equation. So 8 sine squared theta plus 6 cos theta minus 9 equals 0. And we've got that bit there, theta is from 0 to 2 pi, and that's the radian equivalent of 0 to 360. So what we're going to do is solve this equation. So all we're going to do is proceed in the same way as normal. So first job would be to replace the sine squared with a 1 minus cos squared. Hopefully you remember that from your year 1. So we're there. Do a bit of filling around and multiplying out, and we end up with that quadratic. Now we're going to go about solving the quadratic as normal, so that's nothing changes except the last step when we start describing the size of our angles. So we've got cos theta equals half, or cos theta equals 1/4. So therefore theta is cos the minus 1 at half, and at this point this way you would grab your calculator, and what you need to do is put your calculator into radians mode. So you'll need to figure out how to do that. You'll get at it via the setup menu. And that gives us theta equals pi over 3. Now, we need to now figure out what the other angle is. And I'm just going to do a bit of scribbling over here. Some of you might be cast people. I'm a person who likes to draw the cos curve and have a think. So here's my cos curve as per normal. All I'm doing different is saying, well, that value there that was 90 degrees, I'm going to do it in a different colour. Now that value there is now, that's pi over 2. That value there, which was 180, that's now pi. That value, that's 270, 3 pi over 2, and over here we've got 2 pi. So what we need to do is work out, we've got pi over 3, so we've got half, that's there. So that value there, that's our pi over 3. We need this value here, and as we know from the symmetry of our curve, that distance is the same as that distance. So therefore, that value is going to be 2 pi minus pi over 3, which is 5 pi over 3. So my other value is going to be 5 pi over 3, and that's where I'm getting that 2 pi minus pi over 3. If you're a person who's just entirely comfortable with doing your trig curves and you're happy going 360 minus for the cos curve, then 2 pi minus is the trig equivalent of, it's the radian equivalent of that. Okay, same thing now, we're going to go, theta is cos the minus 1 of 1/4. So theta is 1.318. That one is not one of our standard angles, so you end up getting it as just as a decimal. But again, it doesn't mean you've got to do anything differently. To get to the other angle, we're going to go 2 pi minus 1.318, and that gives us our other angle, which is 4.965. You will find to begin with that you're going to spend a lot of time converting all these numbers and thinking still in degrees, because you've been programmed to work in degrees since you first introduced the idea of angles way back in primary school. But over time, your brain will settle down and start becoming much, much more comfortable and familiar with radians. So rather than having to constantly refer back to degrees, you'll be able to figure it out just as it is. Okay, cool.